29th of May, 1660. A tumultuous welcome from the people of London. King Charles II's return from exile and the restoration of the monarchy. This was also the start of a new era of English scientific and mathematical research. For now, an organization could be formed for the promotion of the physico-mathematical experimental learning. The Royal Society was soon granted its Royal Charter, but to appreciate its significance and aims, we need to go back 60 years to the start of the century. Sir Francis Bacon and other intellectuals were greatly concerned by the state of learning at that time. They felt that it was being hindered by the traditional philosophies as taught by the universities. These philosophies were based on a system of logic expounded by Aristotle, by which assumptions are made, and from these assumptions, conclusions are drawn. Bacon argued that if the original assumptions were at fault, then the deductions must be unsatisfactory. However, the state of academic learning was such that long-held assumptions were not being questioned. Bacon instead proposed a radical plan of work, his Instauratio Magna, by which it would equip the scientist to pass, he said, beyond the confines of classical science. Thus, the ship in his frontispiece passed through the Pillars of Hercules into the uncharted regions ahead. The foundation of Bacon's plan is what he calls the natural history. This represents the facts of nature from which the new science would be formed. Bacon outlined a program of scientific observation and experiment to obtain the basic incontestable facts upon which all else would depend. In his New Atlantis, written in 1626, Bacon envisaged a scientific college, Salomon's house. Here were laboratories and instruments, and observers and experimenters, and others to draw from this work and formulate nature's laws. The New Atlantis and Bacon's other writings aroused great interest among the learned. But could Salomon's house be realized? However, even before this, a merchant, Sir Thomas Gresham, had been deeply concerned by the poor state of adult education in London. He left a substantial sum of money to set up a college. In 1598, Gresham College opened to the public. Here, citizens could attend lectures on a range of arts and sciences, including geometry and astronomy. It was above all designed to introduce practical applications of mathematics. Henry Briggs, professor of geometry, was the first to popularize the use of logarithms. These replaced the task of multiplying two numbers by the much simpler task of adding two other numbers. The inventor of logarithms was a Scotsman, John Napier. Napier thought of two lines, one of finite length, the other stretching away to infinity. Now he considered 2 points, P and L. They both start moving at the same speed, and L just keeps on going at that speed. P, however, is slowing down. Its speed is equal to the distance it still has to go, its distance from the point Q. So when it's halfway between P0 and Q, it's only going at half its original speed. Now for the definition. Freeze the action. The distance L has traveled is called the logarithm of the distance P has yet to go. Napier produced tables of logarithms of numbers using this model. Here's what you had to do to multiply two numbers together. You take the logarithm of the first number, add the logarithm of the second, then subtract the logarithm of the number 1. Then reading back from the tables, you get the product. However, it was awkward to subtract the logarithm of 1 in all the calculations. Henry Briggs simplified the problem by improving the definition of logarithms. Now, the logarithm of the product could be obtained simply by adding the logarithms of the individual numbers. And in this way, he popularized the use of logarithms for tradesmen, craftsmen, and seamen. And these are the tables which Henry Briggs compiled and promoted at Gresham College, calculated with great precision to 14 decimal places. The use of logarithms was soon made more simple by incorporating them in an instrument. Alan Chapman takes up the story at the National Maritime Museum.
When Edmund Gunter became Gresham Professor between the years 1619 and 1626, he did a great deal to popularize the use of logarithms and other devices for mathematicians, astronomers, and navigators. One of the key things which he developed was an instrument which came to be known as the Gunter scale or the Gunter scepter. It was indeed an early precursor of the modern slide rule and allowed one to make elaborate mathematical calculations. I'm going to demonstrate a simple example, the multiplication of the number 2 by the number 3. One required a pair of compasses or dividers to make the calculation. All that one required to do was to first of all strike off the number 2 on the scale. 2 3s are 6.
During the 1630s and 40s, the professors of Gresham College continued their program of teaching and made great advances in applying mathematics to problems of navigation and surveying. Gresham College was not the Salomon's house of Francis Bacon, but some of its professors and other science lovers were becoming interested in the new philosophy. John Wallis later recalled meetings in London. About the year 1645, we did meet weekly, sometimes in Wood Street, sometimes at Gresham College. Our business was to consider of philosophical inquiries, as anatomy, geometry, astronomy, navigation, statics, magnetics, mechanics, and natural experiments. But England was in turmoil. The Civil War was raging, with Oliver Cromwell holding the southeast of England. In June 1645, the Parliamentarian army won the Midlands at the Battle of Naseby, and 1 year later captured the final royalist stronghold at Oxford. With Cromwell now in full control, known royalist sympathizers were ousted from the universities of Oxford and Cambridge. Several members of the group meeting at Gresham College were appointed in their place. John Wallis was appointed civilian professor of geometry at Oxford, and John Wilkins, warden of Wadham College. Under Wilkins' leadership, the college quickly gained a reputation for freedom of thought. The philosophers who had moved from London now met weekly in Wadham College, joined by others who were interested in the new philosophy. In 1651, the members of the informal weekly gatherings formed the Philosophical Society of Oxford. It would soon include many who were later founders of the Royal Society. Robert Boyle was a member, as were Thomas Sprat, the first historian of the Royal Society, and Henry Oldenburg, its first secretary. Christopher Wren also attended the meetings and studied mathematics at Wadham. In 1663, Wren was entrusted with his second architectural commission, the Sheldonian Theatre, Oxford University's principal assembly room. His ability to do mathematical calculations was qualification enough for him to take on an architectural contract. Wren chose to design his assembly room in the style of a Roman theatre. But the open-air theatre of ancient Rome was not practical in Oxford. Wren was able to design this completely flat roof, totally without supporting columns. But to achieve this, he had to solve the problem of suspending the flat ceiling. Fortunately, Wren was able to look back to his student years at Wadham College for inspiration. For John Wallis had addressed this very problem in the 1650s. He had constructed a model and also calculated its load-bearing capacity. This was most ingenious. The length and breadth is much greater than any of the individual beams, and it is totally self-supporting except at its edges. So, at the center, we have 4 beams, each supporting one of the others at one end. The other ends are supported by further beams. These are then supported at the ends by others, and so on, until the edges are reached. He recognized the symmetry, and he labeled all 4 corners of the central square A, both to refer to position and the weight that the supporting beam carries at that joint. Other joints were labeled accordingly. Then to calculate the weight on this joint A, he realized that this is made up of 3 components: a proportion of the weight of the beam lying between A and B, a proportion of the weight at this other point labeled A, and a proportion of the weight at C. Now the weight of the beam AB he sets equal to T. The weight supported at this point A is just A. At the point C is just C. Now he needed to work out the proportions of these weights acting at the upper end of the beam AB. He arrived at this. Adding these up and setting them equal to A, the unknown weight at the top of the beam AB, he gets this equation. In a similar way, he derived equations for every other joint in the model.